Okay, so this last unit, the main topic is vector calculus. It's not as scary or terrifying as it sounds. So we'll start with some basic stuff that we need to talk about. First, we're going to talk about vector fields. Okay, and vector fields will help us focus on. Actually, I need a different color. On the mathematical description for flow. So anything that flows, we'll be talking about, or this is what all this applies to. For example, let's see if I can. Oh, awesome. Of course they took the adapter. Let's see if I can just pull this up. Calc 3, 15. Do I really not have? There's that example. I'll pull these up in a second. Well, that's not good.
You can do it too. That's how you do it. I do it on
in physics.
thinking.
Maybe I'll just go to the internet. Just do that.
Go to the internet.
I actually had some examples pulled up in my folder. I don't know if it got erased because it was large.
Monday with Wait, what? One second.
Okay. Come on.
See, I think we should do more there. You really don't.
222.
So then you do this in prospect? Yeah. Probably do it in prospect.
What would you do? Like, what would you focus on?
Yeah.
Just like low weight on a rep, or just
Like body weight.
Oh, bad.
Oh, and that like, is it called like, use vector fields for like calculating your
Anything that moves, basically. So here's one example. These arrows, this is actually great because you talked about slope fields in calc, right?
Yeah.
Okay. It's similar to what you do with slope fields, but when you actually sketch a vector field, the vector field is representative of how large the vector is at that point. So for example, what is this an example of, by the way? Okay. If you're on the outside here of the hurricane, you can kind of see that the wind is pushing this way a little bit, but not that much, right? And as you get closer to the center, you see these vector arrows get larger, right? So that tells you that there's more magnitude there, okay? So this tells us, this paints a picture for us. It tells us exactly what kind of movement there's going to be, if there's particles or if there's things going into that system or that vector field, okay? And you can kind of get an idea. We'll talk about curl, which is something that we'll define probably tomorrow, and divergence, just by looking at a picture like this, whether there's going to be divergence or where there are points of divergence and where there's curl. Okay. Some other examples. Are you serious?
Hooray, it's legal.
Cannot execute binary file. You know what? Let's try this one. Okay, here's another example of a vector field. If you're in physics, this should look somewhat familiar. Electromagnetic field, yep.
So this will come back to quantum.
Is this one? Oh, no. That's from last year. Let's see.
Yeah.
I actually had a pretty cool one with a car somewhere that talked about the aerodynamics and how the wind, the air flowed around it.
Yeah, like car,
Yeah.
yeah, just put car.
That does not seem.
I think the first
I don't
one's
see
definitely.
it.
I think probably.
We could see it. Maybe like settle back.
Nah.
Maybe.
I mean, you can. This is kind of it. I mean, this is not that great. These are actually the streamlines, but you can kind of see, you know, a vector field here, but this isn't that great. Anyway, we'll talk more about this later. If I can find where those images went, those are pretty neat. I'll show them to you. Anyway, let me disconnect and go back to... Hi.
Hey, I'm going to steal this plug. Are you using it? This loaner plug?
No. You're on YouTube now.
Am I?
Yeah?
Me?
Yeah.
For real? On what?
Well, you're not on YouTube yet, but you will be.
Oh, well, that is super... Oh, because it's recording right now? Well, that is so exciting.
That's for now Tuesday.
So we just recorded like us looking for
Yeah, there's like 5 minutes of blank stuff going on with us talking right now. Okay.
So what happens when you miss one?
Yep. Deal with it. All right. So we've seen some examples of vector fields. Airflow or wind. Any fluid flow. Oh, I had another one like where it showed ocean currents and like that was pretty nice to see that. But anyway, anything that moves, that flows, I mean, that's what we're talking about here. Electromagnetic fields. Okay, so lots of real-world applications. And now, in this unit, I like this unit a lot because it brings back some of the stuff that we've talked about earlier. And you're going to start to see where we can use some of this stuff. So here's the formal definition for a vector field. So I guess we should write, this is a vector field definition. The notation is something like this. You have a force vector that will be defined in terms of a function for the I and j components. In other words, at each point, there's a vector f that depends entirely on x and y. That's how we figure out what the vector looks like at that point. So we'll sketch some pretty basic ones. Let's say we have the vector field f equals xi. How do I figure out what the vectors look like everywhere in the xy plane? What can I do? Plug in all the points in the xy plane. Now, you don't have to do that. This is only dependent on what? X. So let's actually get the easiest one out of the way. On the y-axis, what's x equal to?
0.
So there is no vector there. We have a 0 vector. So if you are standing on the y-axis, nothing is happening. Okay? If you go over to x equals 1, plug in 1, then everywhere on this vertical line you have a vector with 1 for the x component, and then what's the y component?
0.
So basically you just draw a vector that's 1 unit long, and as we go further out, let's actually go to 3, because it'll be easier to draw. At x equals 3, how big is the vector there? 3 units, so we're going to go from 3 to... This is actually a very detailed sketch, but the idea here is that you need to know that as you go further to the right, the vectors get larger.
So, like 2 would overlap with 3.
Right, and it's hard to just draw them all in there, but they're there. What happens on the negative side? Yeah, it's just the opposite direction, so... And again, this doesn't have to be perfect. As long as you get the idea that as you go further out, these get larger. Let's try one more. This one's a little harder to sketch. But once you do a few of these, you kind of see what the pattern is going to be. There's really only one spot where there's a vector with magnitude of 0, right? That'd be at the origin. Now, if you go to y equals 1, y is 1, x is 0, right? So we have a vector pointing 1 unit to the right. Because y is 1, x is 0, right? So it's flipped. And as we go further up, that seems to be what's going on here. Now let's look at, we can go the other direction. If I go this direction, at 0, negative 1, it's the same idea. 0, negative 2, we just get a little larger pointing the other way. Let's try the point 1, 1. At 1, 1, both components are 1, so you go out 1, up 1. So it's going to be pointing something like that. at 1, 2, the x component is 2, the y component is 1. Well, sorry, I said that backwards. Since y is 1, we'll go over 1 and up 2. So actually what happens is that these vectors start to get larger and point this way as we get further out. And I mean, you can kind of see at 2, 2, 3, 3, and so on. Along the line y equals x, the vectors are going to be pointing that direction. So we're almost there. Let's see what's going on maybe over in the second quadrant. So in the second quadrant, actually we could probably use this line. We're going to have a similar line over here at y equals negative x. Do you guys see what I'm talking about? So if I'm at, let's say, 1, if I go to negative 1, 1, negative 1, 1 means actually 1, negative 1.
Wait. -1.
So at the point negative 1, 1, what vector does that translate to?
1.
1, negative 1. So we're going to go over 1, down 1. Does that make sense? It's tricky when it's flipped around like that. And you can kind of see that it's the same idea. This way will point in this direction. So you kind of have some basic boundaries here. Did we do 1, 0 yet? No, we did not. 1, 0 becomes, let's see, 0, 1, so we're pointing that way. 0, 2 points this way. You can kind of see, do you guys kind of see what's going to happen here?
It's like shooting to the middle. The angles.
Yes.
I don't get how.
So now I'm just winging it, to be honest.
So when it point towards the axis on the.
So I'm using, it's almost like a hyperbola. I'm using these as like the asymptotes, if you kind of think about it, and everything's just kind of going around this way. So the flow of the field, you guys see it there? Based on the few examples that we did, you can see it right here. This one, I have enough information there to say that it's going to kind of go like that.
Mr. G,
Yep.
wouldn't the quadrant that you're working in right now, wouldn't it go the other direction? Because,
So you have to follow the arrow, otherwise you go
No,
down
but-
direction.
wouldn't the vectors...
Which quadrant are we talking about?
The fourth.
Fourth, yes.
Wouldn't they go the opposite direction? Because you have like,
So give me an example of a point.
1, negative 1.
1, negative 1. So at 1, negative 1, that translates to what vector?
Negative 1, 1.
So you go over left 1 and up 1. Does that make sense? Move on.
There's a particle moving through this field.
Mm-hmm.
What would it do when it reaches the axis? The axis.
You just stop.
Or the y-axis.
When it reaches the y-axis?
Or when
Well, it depends on where it starts. That's an excellent question. So I mean, if we're starting here, then one could say theoretically that it's just going to kind of move this way and then eventually get closer and closer to that y equals x line. Does that make sense?
So what would it do if it reaches the 0 vector?
Well, it wouldn't.
What if they got put in
If it starts there, it stays there. If it's not there, it's going to get pushed along. Does that make sense? Okay, so that's a good question. And actually, this also ties into work. The work done by a vector field in moving something, which we'll talk about later as well. Okay? So we kind of see what's going on here. And you get the idea. Okay, Tyler?
Isn't this kind of like the contour plot to to a hyperbolic tabloid?
Mm-hmm. It looks just like it, except now we have directions attached to it.
Is there a caption?
There is. That's all I can say, pretty much. Okay. So some other notation. So if you see a capital F, you need to know that's a vector field. If you see capital F of xy, that's a vector field. If you see capital F of xyz, now we just have a three-dimensional vector field. And the other one is, if we associate x and y with the radius vector, then we could also write it as f of r. So that would be all the possible ways to denote a vector field. Okay, first objective's done. Inverse square fields are a particular kind of vector field. And probably the easiest way to explain, is everybody good with this page? And probably the easiest way to explain where they come from is to actually start with Newton's law of gravitation, which is physics experts. Well, I could just tell you guys. It's G M1. I don't know how you write it. M1, M2. Okay. We're going to write it as the force is going to equal the gravitational constant, little m, big M.
Oh, is this one?
And then, I don't know if you called it R or distance or what have you, but okay. But it should look familiar. Okay, so this is essentially, we have particles, if you're not familiar with this, particles with masses little m, big M, and they attract each other with force F. Okay, and then r is the distance between the two particles. So if we have something like this, let's actually focus. Let's say this is our origin. Okay, so suppose we have this scenario, and let's call this our radius vector. Then what we could say is a couple things. One, that the force exerted by the particle of big M, mass big M, to the other one, to the particle of mass little m, is in the direction of a unit vector. So we're going to bring that in. And now, these, if we're talking about the big mass, these exert attractive forces, right? So we're going to say is that this is technically attracting, so the force would be pointing towards the big mass. Does that make sense? So what we're going to say is that the direction is actually going to be minus r, And if we want a unit vector, we can divide by its magnitude like we did in chapter 11 and 12. So this is the direction of the force. And now if I'm using this equation, we could say that not the magnitude of the force, but just the force could be written as minus g capital M little m, so nothing changes there. But now this will be magnitude of r squared. And then the direction just gets attached, no more negative, sorry, just gets attached to this. This doesn't change the size of the vector, it just gives us the direction.
So are we multiplying by that?
Yes. I just have a blob there because I messed up what I was writing. So it's the same law, but now we're attaching a direction to it, okay? And this gives us the inverse square field format. So an inverse square field is going to look generally like a vector field f of r. We're going to call all of this just a constant c. We're going to lump together the magnitude of r squared and magnitude of r to make it magnitude of r cubed. And then we still have this other r. So this is what an inverse square field looks like. Okay, so this is where it's coming from. Mathematically, you know that something that's inversely proportional to a square, you need to divide, right, by the square of that variable. Does that make sense? So technically, this is an example of one. It's just now we have a vector attached to it. So when you have this r out here, I know this is cubed, but you can kind of remember it that technically it still came from this equation over here. Okay? This is a good place to stop. Tomorrow we'll talk about gradient fields, conservative fields, divergence, and curl.